Grounding provides a low-resistance path for fault currents to flow, reducing the risk of electrical shock and electrocution. Grounding helps protect against lightning strikes by providing a path for the electrical current to flow into the earth. Grounding helps prevent damage to electrical equipment by providing a path for surge currents to dissipate. The National Electrical Code, or NEC, and the National Electrical Safety Code, or NESC, both require grounding of light poles. The NESC and NEC have slightly different grounding requirements for light poles. The NESC requires a driven ground rod at each pole if the soil resistance exceeds 10 ohms. The NEC does not specifically require a ground rod, but it does state that the grounding electrode system shall have a resistance to earth of 25 ohms or less. The NESC requires a ground rod at each pole primarily for safety reasons. In higher resistance soil, a ground rod provides a reliable path for fault currents to flow into the earth, reducing the risk of electrical shock and electrocution. There is an ongoing effort to harmonize the NESC and NEC requirements for grounding. The goal is to ensure that electrical installations are safe and code compliant regardless of whether they fall under the jurisdiction of the NEC or NESC. While the NESC and NEC may have slightly different grounding requirements for light poles, both codes recognize the importance of grounding for electrical safety and equipment protection. In situations where the soil resistance is high, a driven ground rod is essential to meet the safety requirements of the NESC. When dealing with a 40-foot aluminum pole with the base set in precast concrete and the concrete is cured and dry, the resistance can be high, as aluminum oxide essentially insulates the pole from the concrete. If the supply is 2400 volts, series primary to individual transformers, with no equipment, ground wire, and ground fault detected by residual current relay for detecting a ground fault, the absence of a driven 5/8 inch by 10 foot rod at each pole will prevent the residual fault detector from functioning, as the pole will elevate to 2400 volts through capacitance coupling. There are many reasons for grounding light poles. Firstly, grounding provides electrical safety. Secondly, grounding provides lightning protection. Thirdly, grounding ensures equipment protection. And fourthly, grounding helps ensure code compliance. The NESC and NEC, while both addressing electrical safety, sometimes differ in their specific requirements. Understanding these differences is crucial for ensuring safe and compliant installations. The NEC mandates that the grounding electrode system should have a resistance to earth of 25 ohms or less. This requirement ensures that fault currents have a low impedance path to return to the source, facilitating the operation of overcurrent protection devices. The NESC, particularly in high resistance soil conditions exceeding 10 ohms, mandates the use of a driven ground rod at each pole. This provision ensures a reliable path for fault currents to flow, mitigating the risk of electrical shock, especially in environments where the soil's natural conductivity is poor. High soil resistance impedes the flow of fault currents, increasing the potential for dangerous voltage levels on exposed metal parts. A ground rod provides a direct low-resistance path to earth, minimizing this risk. The ongoing harmonization efforts between the NESC and NEC aim to reconcile these differences, promoting uniform safety standards across different jurisdictions. The intention is to create a more consistent and easily understood set of guidelines for electrical installations. When evaluating the need for grounding, several factors must be considered. These include the soil resistivity, the presence of other grounding electrodes, and the specific requirements of the applicable electrical codes. Soil resistivity is a measure of how well the soil conducts electricity. High soil resistivity indicates poor conductivity, necessitating additional grounding measures such as ground rods. The presence of other grounding electrodes, such as those connected to nearby buildings or structures, can affect the overall grounding system performance. It's essential to ensure that all grounding electrodes are properly bonded together to create a common ground potential. Compliance with the NEC and NESC is mandatory for all electrical installations. Failure to comply can result in fines, penalties, and potential safety hazards. It's crucial to consult the latest versions of these codes and to engage qualified electrical professionals to ensure compliance. In conclusion, grounding of light poles is essential for electrical safety and equipment protection. While the NEC and NESC may have slightly different requirements, both codes emphasize the importance of providing a low impedance path for fault currents to flow. In high-resistance soil conditions, a driven ground rod is necessary to meet the safety requirements of the NESC and to minimize the risk of electrical shock. The 5/8" by 10" ground rod provides a reliable path for fault currents, ensuring the proper operation of ground fault detection systems and minimizing the risk of electrical hazards. It is important to understand that relying solely on capacitance coupling for ground fault detection is not a safe practice, especially with 2400-volt systems. Capacitance coupling can create a pathway for voltage to build up on the pole, posing a significant shock hazard. The grounding rod provides a direct connection to earth, preventing this voltage buildup and ensuring the safety of anyone who may come into contact with the pole. The absence of an equipment grounding conductor exacerbates the risk, as it removes an alternative path for fault currents to return to the source. In this scenario, the ground rod becomes even more critical for providing a reliable ground connection. The residual current relay is designed to detect ground faults by monitoring the imbalance between the current flowing in the supply conductors and the current returning through the neutral conductor. Without a proper ground connection, the fault current may not be sufficient to trip the relay, leaving the pole energized at a dangerous voltage. The ground rod ensures that the fault current is high enough to activate the relay, quickly disconnecting the power and preventing electrical shock. Proper grounding techniques involve not only installing the ground rod, but also ensuring that it is properly bonded to the metal structure of the light pole. This bonding creates a continuous electrical path, minimizing the impedance between the pole and the earth. The connection should be made with a heavy gauge conductor and should be protected from corrosion to ensure its long-term effectiveness. Regular inspection and testing of the grounding system are essential to verify its integrity. This includes measuring the ground resistance to ensure that it remains within acceptable limits. If the resistance is too high, it may be necessary to drive additional ground rods or to improve the existing connections. In areas with high soil resistivity, it may be necessary to use chemical ground rods, which contain chemicals that leach into the soil and improve its conductivity. These rods can significantly reduce the ground resistance even in very poor soil conditions. Another important consideration is the depth at which the ground rod is driven. The deeper the rod is driven, the lower the ground resistance will be. In general, the rod should be driven to its full length, ensuring that it makes good contact with the surrounding soil. The use of a ground rod is not a substitute for proper insulation and other safety measures. It is just one component of a comprehensive electrical safety program. It is important to ensure that all electrical equipment is properly insulated and that all personnel are trained in safe work practices. In addition to the NESC and NEC, other standards and regulations may apply to the grounding of light poles. It is important to consult with local authorities and to ensure that all applicable requirements are met. Grounding practices should also consider the potential for lightning strikes. Lightning can generate extremely high voltages and currents, which can damage electrical equipment and pose a significant shock hazard. A properly grounded light pole can provide a path for lightning current to flow into the earth, reducing the risk of damage and injury. Lightning protection systems typically include air terminals, down conductors, and grounding electrodes. The air terminals are designed to intercept lightning strikes and to direct the current to the ground. The down conductors are heavy gauge conductors that connect the air terminals to the grounding electrodes. The grounding electrodes provide a path for the lightning current to dissipate into the earth. The design and installation of lightning protection systems should be performed by qualified professionals. Proper grounding is essential for the safety of electrical systems and for the protection of people and property. It is important to understand the principles of grounding and to follow all applicable codes and standards. By taking these precautions, the risk of electrical shock and other hazards can be significantly reduced. The importance of grounding in electrical systems cannot be overstated. It serves as a fundamental safety measure, providing a low impedance path for fault currents and protecting against electrical shock, equipment damage, and fire hazards. A well-designed and properly installed grounding system is an essential component of any electrical installation, ensuring the safety and reliability of the system. In the context of light poles, grounding is particularly critical due to their exposed location and potential for contact with the public. Light poles are often located in areas where people walk, drive, or otherwise interact with their surroundings. As such, it is essential to ensure that they are properly grounded to minimize the risk of electrical shock in the event of a fault. The grounding of light poles is governed by various codes and standards, including the NEC and NESC. These codes provide specific requirements for the design, installation, and testing of grounding systems. It is important to consult the latest versions of these codes and to engage qualified electrical professionals to ensure compliance. The NEC, published by the National Fire Protection Association, is the most widely adopted electrical code in the United States. It provides comprehensive requirements for the safe installation of electrical wiring and equipment. The NESC, published by the Institute of Electrical and Electronics Engineers, is a standard for the design, construction, and maintenance of electric power and communication lines. It is widely used by electric utilities and other organizations that operate overhead and underground electrical systems. Both the NEC and NESC recognize the importance of grounding for electrical safety. They provide detailed requirements for the selection, installation, and testing of grounding electrodes, grounding conductors, and bonding connections. The grounding electrode system is the foundation of the grounding system. It provides a connection to the earth, allowing fault currents to flow back to the source and activate overcurrent protection devices. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes. Ground rods are the most common type of grounding electrode. They are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. Ground plates are flat metal plates that are buried in the earth. They are typically used in areas where it is difficult to drive ground rods, such as rocky or paved areas. Underground metallic water pipes can also be used as grounding electrodes. However, they must be in direct contact with the earth for at least 10 feet and must not be coated with an insulating material. The grounding conductor is a conductor that connects the grounding electrode system to the electrical equipment. It provides a path for fault currents to flow from the equipment to the grounding electrode system. The grounding conductor must be sized according to the size of the electrical service. The bonding connection is a connection that electrically connects all metal parts of the electrical system together. This includes metal enclosures, raceways, and equipment housings. The bond-in connection ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. The bonding connection must be made with a conductor that is sized according to the size of the electrical service. The grounding system must be tested periodically to ensure that it is functioning properly. The test typically involves measuring the resistance of the grounding electrode system. The resistance should be low enough to allow fault currents to flow back to the source and activate overcurrent protection devices. If the resistance is too high, it may be necessary to install additional grounding electrodes or to improve the existing connections. In addition to the code requirements, there are also several best practices for grounding light poles. These include using corrosion-resistant materials, protecting grounding conductors from physical damage, and ensuring that all connections are tight and secure. Corrosion-resistant materials, such as copper or stainless steel, should be used for grounding electrodes, grounding conductors, and bonding connections. This will help to prevent corrosion and ensure the long-term effectiveness of the grounding system. Grounding conductors should be protected from physical damage by installing them in conduit or other protective enclosures. This will prevent damage from being struck by vehicles or other objects. All connections should be tight and secure to ensure a low impedance path for fault currents. Loose connections can increase the resistance of the grounding system and reduce its effectiveness. The grounding of light poles is an important safety measure that helps to protect people and property from electrical hazards. By following the code requirements and best practices, the risk of electrical shock and other hazards can be significantly reduced. Proper grounding is not just a matter of code compliance. It is a matter of safety and responsibility. By ensuring that light poles are properly grounded, a safer environment can be created for all.